This is worth talking about because even and odd functions are something that kind of come back in trigonometry. But these are examples of even functions right here. This is the absolute value of x, that's x squared. They're called even functions. They're even functions because both a positive x and a negative x have the same exact what value? Y value. That's what makes them even. Just that right there. Now, the function rule itself says that f of x is equal to f of negative x. And there's that good old funky function notation, which just keeps funking with your head. You don't funkin' like it, do you? Nope. It'll click as you get older, kids. And it will. You got to keep doing it, keep doing it. But if you can understand the graph, that makes sense. It's saying that the y value, because isn't f just a fancy way of saying y? The y value for a positive x is the same as the y value for a negative x. That's what makes it an even function. The odd function is a little bit different. These are examples of odds. But let's say that that's some positive x and this is some negative x. Well, up here, the y is positive, and down here it's what? Negative. These are odd functions. Okay? Function rule for that says that f of x is equal to, hold on. Function rule is actually a little bit different than what the graph suggests. Function rule says that f of negative x is equal to negative f of x. It's a little bit different than what the graph suggests. The first one's easy to pull the function rule from, the second one's not so easy. I want to make sure I'm lining up with your book because I'm actually thinking about trigonometry when I do these. F number at negative x is also a big deal. Yeah, I'm going with it. We're not going to go into too much detail on these, but determine if the functions are even or odd from the graph. That ought to be a little bit easier. This guy right here, based on what you see, are the y values the same for any random x? Does that make it even or odd? Makes it even. Now, how about the guy at the end? Not the middle, the guy at the end. Is odd. If you have some positive x and positive y up here, you have some negative x and some negative y down there. That's an odd function. How about the guy in the middle? Is he even? I don't think those are the same x values, nor the sign. Kids always forget about the neither option. The function is neither even nor odd. Kelly said even, but say this is 3. Is that pointing back there negative 3? No, they're not the same x values, ignoring signs. The y values might be the same, but the x's aren't lining up like they should. So that's a neither. All right, then we've got determining, identifying algebraically. I want to look at something first, make sure I wrote down the right function rule. I'm actually thinking up here about our odd rules from trigonometry. And I want to make sure I'm applying the right ones algebraically. So give me a second. Just want to make sure I'm giving you the right rule. Should be. Works in trigonometry. Ah, I was right. Good. All right, so here we're tasked with identifying these things as even or odd algebraically. Now I'm going to go ahead and do example B because I'm pretty sure I know what the answer to that one is. I'm going to jump down to example B. All we got to do is apply our test of symmetry. Really all we have to do is two things. We have to plug in, or we have to find, let me say, f of negative x and compare it to both positive f of x and negative f of x. It's really all you have to do. Now, what does it mean to find f of negative x? To find f of negative x, we let x equal what? Okay, let's go back to something like f of 3. How do you find f of 3? You let x be 3. Everybody knows that. So why the wall when a question is asked like this? What is f of negative x? You let x be negative x. Everywhere you see an x, what's it become? Negative x. Just make sure you use parentheses. And I am doing example B. So 2 parentheses negative x all squared minus 3. That's what it means to find f of negative x. When you do the little math on that, what do you get back? You get the same thing back. So what you just found is you found that f of negative x is equal to the original function itself. So what kind of symmetry does it have? Even. Oh, it's an even function. I'm talking about symmetry, something else. You know, if you're curious about something, you can just always take a look at the graph too. If you don't understand or you're a little curious about the algebra in the beginning, you can just take a look at the graph and see what the graph looks like. Would you say based off the graph that thing was even? Yeah. So use that to support yourself. Don't use that as how you find the answer. Use it to support and justify what you came up with algebraically. That guy right there is also even. X squared plus 5x. Let's look at that one. So let's find f of negative x. That's done by replacing x with what? Oh, that's a cube, isn't it? All right. So you replaced your x with your negative x. What's a negative x times a negative x times a negative x? What is it? Negative x cubed. And then we have minus 5x, because positive 5 times negative x is minus 5x. Now, does that look like the original function? No, so it's not even. But you also need to compare it to negative f of x. So you're going to find negative f of x. Negative f of x happens when you multiply this thing by what? Negative. I don't know that I'll show this, but you would just take the entire function and multiply it by a negative. And if you thought about distributing that negative, would these two guys match? Yeah. So what kind of function is it? Is it an even function or odd function? It's odd. It's the function rule. F of negative x equals negative f of x. It's odd. I never actually saw this in high school. I remember seeing it on a GRE practice test for graduate school. So I made it all the way through college without ever actually seeing this stuff. It showed up on a GRE. That's when I had to figure it out. But you want to just look at something like even. You look at the exponent, you see 2, you're like, that must be even. That's not what it means, kids. It's not. You know, there is a test after ACT that you'll take if you're going to graduate school. It's called the GRE. All right, some other good stuff in here. Determining where a function is increasing, decreasing, or constant from its graph. This is really not a hard skill if you use words. It's a hard skill for some if you use what's called interval notation. That makes it hard for some. All right, so we've got a couple of questions here. First one is, where is this function increasing? And when you answer these things, you answer it with x values. Would you agree that based on where my 2 fingers are here, that graph is increasing? All right, so it increases from x equals -4 all the way until where? That's all fine and dandy, but are you going to respond with words? No, you're not. You know that. Do you understand the words, though? As long as x is between -4 and 0, this graph is increasing. There's a couple of ways you can write that. You can use set builder notation, which would say all values of x, so long as x is between -4 and 0. That's just an inequality, because x is trapped between those 2 things. Or you could just use interval notation. I never leave enough room, do I? Or the interval that goes from -4 to 0. You guys remember interval notation? This reads x is trapped between -4 and what? 0. Well, there's 2 ways of answering that. Just be comfortable with both. All right, where is it decreasing is the next question. I think it's decreasing here, and I think it's decreasing over there, because it's going downhill. Does anybody have a problem with that idea, that those are 2 spots where it actually decreases? You do have a problem with that idea? You don't have, okay, good. All right, now write that out in words. Now, let's not do words because I don't have a lot of room. Write this out as inequality. What 2 values is x trapped between over here on the left? -6 and -4. So I'll do set builder notation on this. All values of x such that x is trapped between -6 and -4. What's that look like as an interval? -6, -4. Things worth talking about here. Like, why am I not using the equal sign? Because at this point, nothing's happening. It is neither increasing or decreasing, is it? Not until you move just a little bit over does it start going downhill. And like right here, it's not increasing or decreasing. It just kind of stops. That's where it's at. All right, where is it constant? Anybody know where it's constant? 0 to 3, where there's no change in y. Constant means no change in y. And Daniel's right. He says between 0 and 3. Can anybody just go straight to the interval? It's between 0 and 3? 0, 3. What were they wrapped in? Parentheses. You know, I actually did not finish the one above, did I? I did not. It was also decreasing over here. Yeah, I'm just going to scratch out the inequality. So I am decreasing between -6 and -4, and over here when x is between what? 3 and 6. Remember what goes between them? A u. Let's see here. Let's scratch out that little guy because there's no room anymore. Let's do that little guy. Where is f of x less than or equal to 0? I kind of hate going into so much detail on things, but what does that mean to you? Anybody describe what that means to you in words? Huh? It's where y is less than or equal to 0. Yeah. It's also where the graph is below the x-axis. That's where that's happening. The graph is below the x-axis. Now there's only one little spot where that actually happens. It's right here. What x values make that happen, make that true? -6 and -2. Now look at your symbolism here. Are you going to be using parentheses like we have been? What are you going to be using? Brackets. And if you don't like interval notation, you would trap x between -6 and -2 with less than equal to symbols. I don't have a preference as to what you use. My personal preference is interval notation. It really, really is, because it's just quicker and shorter to write. It really is. I don't know why, but I think it's easier to comprehend too, but that's me. Just be prepared on a test for either one of those to show up. Okay? So you do whatever you think is best, but you need to understand both notations. All right, here's actually the main thing I want to talk about today. It's called local max and local mins. We got way too many slides dealing with these things. But a local maximum is literally a local high point in a graph. There's all this weird math text there, but it is the local high point in a graph. That's all it is. Does everybody have a high spot in their yard at home? Well, that's your local maximum in your yard, isn't it? Okay, it's not a hard concept. Does everybody have a place in your yard that likes to puddle up? A wet spot? Guess what that is? It's your local minimum. That's all that is to it. So, I mean, that's pretty apparent from the graph. You can write something down there if you want, but it's the lowest point in an area of a graph with a local minimum. And we're going to jump down to the example right underneath it, that one. Oh, I guess it's all tied together. All right. I bled through pretty bad, didn't I? Here's our graph that we're using for the next two slides. At what numbers, if any, does f have a local text wrap? Let's say I'm guessing it's maxima. Because B says, what are they? So what x values create local maximas, if any? It's just a high spot in the yard. What's that? X equals 1. This guy right here is a local maxima. This stuff doesn't count. You know, I always tell kids when it comes to maximum and minimum, a maximum is kind of like a hill, and a minimum is kind of like a valley. So this stuff over here doesn't count. Now, if it curved over like that, would that be a local maximum? Okay, so you might add that in your notes. That would look like a local maxima. But it continues on forever, so it doesn't really count. What are they? When a person asks for what are they, they're asking for the y value. So what is the actual value, the height of your hill? 2. All right, at what numbers, if any, does f have a local minimum? There's 2 of them present. What are the x values that create those values? X equals -1 and x equals 3. What are they? 1 and 0. We're not going to talk about the next slide. That's increasing and decreasing intervals. Actually, we should because the infinity symbol shows up. That's probably worth talking about. Part E is list the intervals on which f is increasing. How many increasing intervals do you see? How many, Breton? I see 2. Increasing means goes up, positive slope, kids. There's 2 places this graph has positive slope. Here and here. What's the interval for our first increasing region? What's x trapped between? -1 and what? +1 maybe? The second one we say union with. Second one starts when x is what? 3. Goes on forever to the right, doesn't it? Where does it stop? Stops at infinity. We have good old decreasing. It's kind of a similar one. I'd be glad to, because you couldn't see a thing, could you? So I see 2 areas of downward slope here. And you do need to talk about this from left to right. Isn't that how you read? You know, so you talk about it from left to right too. So you're going to talk about that left interval first, this one over here. Where does this one start when you think about its x values? Starts at -infinity. Falls until it hits an x value of what? -1. And then, you jump around till you start falling again right here. From 1 till what? 3. That's just reading graphs. We got left 7 minutes. Not even that. 3 minutes? Well, crap. So that didn't work out the way I wanted it to. All right, we'll start there tomorrow. I was really hoping to get more than that done. So maybe tonight you start drawing something. Told you on the 11th, you can come in and I'll help you with things. But you need to at least have a drawing by then or I can't help you with anything. You come in on the 11th and you start drawing, that was my day to help you with things. If I get a chance, I'll post some more videos on the classroom, me drawing something. Anybody watch any of that stuff? Huh? Well, I was trying to show you how to draw a tree. Trees are hyperbolas and parabolas. I was working on the all-seeing eye, but then the bell rang. Anybody got anything in particular you'd like to see drawn on Desmos that maybe you want in your drawing that you don't know how to do? Because I'd be glad to do it. Anybody in this room who's not brainwashed by their phone? Got to get your fix. Believe it or not, that is a chemical addiction. That constant need for stimulus.